Welcome to Short Talks from the Hill, a research podcast of the University of Arkansas. My name is Matt McGowan. I'm a science writer here at the university. Today, I'll be talking to Hugh Churchill about two interesting and important projects. Churchill is an associate professor of physics in the J. William Fulbright College of Arts and Sciences. Earlier this year, Churchill and several colleagues here at the University of Arkansas and Montana State University received a $20 million grant from the National Science Foundation to establish the MonArk NSF Quantum Foundry. The foundry will accelerate the development of quantum materials and devices. Churchill also led a project this year to build and test and show you how to build a basic portable air filter that removes infectious airborne particles from indoor spaces. These particles included the respiratory droplets that carry coronavirus. Welcome, Hugh, and thanks so much for being here.
Thank you. Happy to be here.
Before we talk about the foundry, can you define quantum or quantum physics? It's kind of a big, scary word.
I hope I can. So I'll try to give it a shot. And actually, I don't think it should be that scary. But ever since Einstein declared it spooky almost 100 years ago, I think that reputation has sort of stuck. And so I'll do my best to see if I can improve that reputation any. So quantum physics or quantum mechanics was developed to describe and understand the behavior of atoms, which back then had been observed to behave differently than the relatively large everyday objects that we can see and touch as humans. And the word quantum just refers to the smallest possible piece of some physical quantity like energy, and the fact that you can only have multiples of those pieces. So 1, 2, or 3 of those pieces, and values in between like 1.5 or 2.5 are not allowed by quantum mechanics. So for example, lasers require quantum mechanics for their operation. And the fact that you always see laser pointers with one particular color, whether it's red or green, for example, comes from the fact that quantum mechanics requires that the light that comes out of the laser to have a particular energy and not just any energy. But that's actually not the part Einstein thought was spooky. In fact, he helped invent that part. The rest of the story is that quantum mechanics tells us that all objects in the universe, when examined in the right way, are waves. And those waves can interfere with each other, be in superpositions of different possibilities. And here's the supposedly spooky part, become entangled with each other. And okay, admittedly, that probably sounds pretty scary, but really it's not. And I'd like to spend a little bit of time talking about each of those three ideas: interference, superposition, and entanglement, and try to give you some idea of what each of those is about. So interference just means that waves can either add together to make a big wave if a crest lines up with a crest, or they can completely cancel each other out if a crest happens to line up with a trough of the other wave. And so that's just normal wave behavior. And maybe the only hard part is accepting that physical objects can behave that way too. So next up is superposition. And the scary way of talking about superposition is to say that quantum objects can be in two different states at the same time. So for example, there's a thought experiment in quantum mechanics called Schrodinger's cat. And during the middle of the experiment, the poor cat is thought to be both dead and alive at the same time. And obviously that's nonsense. Real cats don't behave that way. The less scary way to describe superposition is just to say that if you have two possibilities, we can call them A and B, then being in a superposition just means that the true situation is best described as a little bit of A and a little bit of B. It's not A and B at the same time, it's just a little bit of each of those possibilities. Okay, so finally we have entanglement. This means that when two quantum objects interact with each other, we can no longer talk about them individually. Instead, we have to talk about the state of the combined system together. And after they have interacted, we say that they became entangled. And so this has some surprising consequences, like the fact that a measurement of one object tells you something about the state of the other object, even if they're on opposite sides of the galaxy, for example. And this is the part that Einstein didn't like. But it's really not so spooky because the entanglement was created when the objects were close together and still interacting. And so I once heard the physics Nobel laureate Frank Wilczek describe the situation like this. It's like you have a box of shoes and you cut the shoebox in half and you send one half in one direction and you send the other half in another direction. And then you open up one of the boxes and you find out that it had the right shoe in it. And so you immediately know then that the other box holds the left shoe, no matter how far away it is. And there's nothing, spooky or surprising about that. It's just the fact that at some earlier time, those shoes were together in the same box, one left shoe and one right chute. But this is actually all old news and was figured out in the first half of the 20th century. The reason there's so much quantum hype right now is that we're really entering a new era in which physics and engineering have both advanced to the point that we can not only understand how quantum objects work, but we can also control them and use superposition and entanglement as resources to solve problems that are impossible to solve with regular computers. So it's not any problem that you could solve with a quantum computer, but a very specific set of problems that nevertheless have a lot of potential for applications in the longer term for example, secure communication and artificial intelligence, and maybe sooner than those applications, because quantum computers run using the same math that the universe runs on, they could be used as simulators of big molecules, and that could be useful for applications in biology, drug discovery, or my own personal favorite as a material scientist, material science.
Okay, let's talk about the foundry now. What is the MonArk NSF Quantum Foundry, and what will it do?
So in this field of quantum computing, we're constantly looking for better components to work with. The problem is that superposition and entanglement are very fragile and are rapidly destroyed after times as short as microseconds. So imagine if your computer's hard drive got wiped 1,000,000 times a second, it wouldn't be very useful. And we think there are a lot of applications for more robust quantum systems by using atomically thin two-dimensional materials. These are materials that consist of only a single sheet of atoms. But the problem is that we actually have thousands of these two-dimensional materials available to choose from, and making devices out of them is really hard. And so it's very time consuming to work through all of the possibilities that we have to find the best ones and the best combinations for particular applications for quantum technologies. And so what we want to do in the MonArk NSF Quantum Foundry is use robots and artificial intelligence to accelerate that process of creating materials and making devices out of them, so that we can more rapidly understand how these materials behave and apply those properties and that behavior to various quantum technologies. And a big part of our effort is that we hope to become really a national resource that researchers from all over can turn to have materials and devices made for them and help accelerate progress in our entire research community and help everybody go faster.
And what will your role be at the Foundry?
So I will be one of the 2 associate directors of the Foundry. We have 2 sites, one at U of A and the other at Montana State University, and our director is at Montana State. And so I'll be the associate director in charge of our operations in Arkansas, working with a big team that includes faculty in physics, electrical engineering, and computer science.
You've been working on another project, and that is building and testing an inexpensive do-it-yourself portable air filter that removes infectious airborne particles from indoor spaces. Can you tell us about this work?
Yeah, I'd love to. So, at the very beginning, I just want to be clear that I'm a physicist and not an epidemiologist or an infectious diseases expert. But, as the pandemic has worn on, it's become increasingly clear to the real experts that to mitigate the spread of the virus, we have to address the airborne transmission route that COVID has. So the idea there is that basically the virus can spread on tiny particles that can float in the air for as long as hours. And so there are various ways that you could deal with that, but one that's relatively easy to implement is to set up an air purifier in a room that will just remove those particles from the air as they are generated. And the best way to do this actually is using HEPA filters of the kind that you find in hospitals or clean rooms that are very efficient at removing particles from air. But there's also a do-it-yourself version that just uses box fans and some regular air filters and duct tape and duct tape. So all stuff you can buy at Walmart and put together yourself. And so as a physicist, I wanted to see if the do-it-yourself version could actually work and how it compares to the much more expensive commercial units. And so I had some tools on hand to measure the particle removal efficiency because in my work with quantum devices, we need clean environments so that those particles, dust particles don't destroy our tiny devices. And also got some help from U of A facilities to measure the airflow. And we were able to see that the do-it-yourself version can actually have performance that's similar to the commercial units and at a fraction of the cost. So it seems like it's really a pretty good option for producing cleaner air. And hopefully, as the final wave, I hope, of COVID winds down, this concept may not seem as urgent, but actually the pandemic has taught us that we need to be taking indoor air quality more seriously to prevent airborne transmission of respiratory viruses, not just SARS-CoV-2, the one that causes COVID, but also flu, for example. And so just as we come to expect clean drinking water to prevent the spread of diseases that can be spread through water, I think in the future, we'll also come to expect cleaner air in our buildings so that we don't become infected with respiratory viruses.
That's great. Thank you. So there's a website where our listeners can learn more about the air purifiers. What is the website, and what can listeners find there?
Yeah, so the website is cleanarair.com. That's cleanarair.com. And I put this together in collaboration with Douglas Hutchings at the Arkansas Research Alliance. And so it includes just instructions for how to make these things. It has shopping lists where you can go on Walmart.com or Amazon and order the parts. And another, in my opinion, important element of it is that we also have a bunch of lesson plans so that if teachers, for example, want to deploy these purifiers in their classrooms, they can find a great appropriate lesson plan to refer to and have one or more activities that explore some of the science behind how these purifiers work or how air moves through the room or things like that, and tie in efforts to mitigate the spread of disease with some of the curriculum that they'll be covering in their classes.
And this has reached teachers and students in the state of Arkansas, but also outside of Arkansas. You mentioned was it one student from Colorado who had communicated with you and you talked to about the project?
That's right. So, the website obviously is accessible to anybody, even though our focus was on Arkansas. And so just last week, I had a meeting on Zoom with a high school senior in Colorado who's going to work on a project for his AP research class, studying, how air moves around in a room using these purifiers. And we've heard from a teacher, for example, in California who helped deploy, 10 or a dozen of these all across his grade at his school.
Thanks, Hugh. And thanks a lot for being here today with us on Short Talks from the Hill.
Thanks for having me.
Music for Short Talks from the Hill was written and performed by local musician Ben Harris. For more information and additional podcasts, visit Arkansas Research. That's arkansasresearch.uark.edu, the home of science and research news at the University of Arkansas.